All right, guys, let's talk some more now about lateral loads. Um, when things don't go right, buildings end up looking like this. No bueno. All right, so let's just walk through lateral load paths. So first off, you have wind that can blow on a structure or inertial forces from seismic. So as the ground moves, the building doesn't move with it initially. And so it's those inertial forces that cause things to be a problem in seismic. Okay, those wind or inertial forces can then span between floors. So this is a portion of wall here. Some kind of wind load puts a point reaction or a line load reaction at each floor level. So we call that floor or roof a diaphragm. Diaphragms are a deep beam. They basically resist those loads. So the load are these filled-in arrows, and then the resistance are these open arrows, and that's what delivers the force from the diaphragm to, say, a shear wall or a moment frame. So once the diaphragms deliver their load to a frame, that wants to tip over. So we might have multiple loads onto a wall or frame. And then the overturning loads are going to be resisted by either the weight of the structure itself or piles deep into the ground. And then there'll be a shear at the ground which resists each of those horizontal shears from either the wind or the earthquake. So if we can't follow a load path in lateral load design that goes from the applied wind load to a member to the floor, floor to the wall or frame, frame to a footing to the ground, then we're going to have a problem. So when I detail or design things, I like to go, like say a wood building, I'll go from like a wood diaphragm to a nail to another piece of wood to maybe a metal clip to another to a nail to another piece of wood, then back into the wall sheathing. It gets that particular. And if you are that particular about it, your buildings are going to be fantastic and robust, which is exactly what you get hired to do. Okay, so we'll talk a little bit about wind loads first. As the wind blows, in this case from left to right, it creates positive pressure on the windward face, negative or suction on the back face, we call that the leeward, and then suction on the side faces. To calc wind, ASCE 7 gives us all of these fun steps. So first we're going to go to the map and determine the wind speed. So this is the wind for category 2. You'll see Utah is between 100 and 105. I just use 105 because I don't want to interpolate, or I can come here to this ATC hazard and put in an address. So I live in Sandy. I can come in here and say, what's the risk category 2 wind speed? They've done the interpolation, 103. Category 3 and 4 are slightly higher. And I can do that for anywhere in the country. So if I zoom out here and drag my pin to Florida, you can see the wind speeds are a lot higher. And it also gives us a warning about being in a wind-borne debris region. So pretty big difference in how we think about that type of structure. Okay, so I get my wind speed. And then I establish my directionality factor. That's usually 0.85, sometimes different depending on the type of structure, but for most buildings and even industrial structures with 0.85. Exposure category. So this is going to relate to surface roughness. So B is urban and suburban areas, C is open terrain, D is flat, unobstructed areas with water. So just look at like a Google Earth type map, and you can see kind of what you're going to be. Topographic factor, if there's a hill leading up to our structure, you can see just by the shape of this wind speed curve, that there's some speed up near the top of a hill, so we want to take that into account. Ground elevation factor. So it turns out the air is less dense the higher in elevation you go. So if you're near Salt Lake, we're 0.86 rather than 1 at sea level, which is kind of interesting. Gust effect factor, typically 0.85. If it's flexible, it gets way complicated. I've never had the privilege of designing a flexible building and don't really anticipate it, but if you get into that, there are sometimes moments where you need more help, and maybe hiring in a wind expert is something worth doing on really big public view type projects. All right, enclosure classification. So if it's an enclosed building, there's some internal pressure, so 0.18 plus or minus. Partially enclosed, so like a garage with a door open, you could have substantial internal pressures. I worked on a project where a big window got blown out, and the building pressurized, lift the roof up, push the window or the walls out, and all that was holding the roof on was a couple trusses at each end that hadn't fully pulled off. So the building was pretty much thrashed, but pretty fascinating to see a building go from an enclosed building to a partially enclosed building and be in pretty bad shape. Okay, velocity coefficient. So depending on our height above the ground, we will design for higher pressures depending on what exposure category we are. So if I am kind of out in the country, not a lot of buildings, not a lot of woods, and my building's 50 feet high, I'm going to have a factor of 1.09. So you find out how tall your building is, what exposure you are, and you can pull that number off pretty quickly. Okay, velocity pressure equation. So you take all of these components that we've just been talking about, plug them in, the velocity is squared. So it's good just to keep that in mind, that wind speed is squared as it relates to pressure, and you can plug and chug and get your velocity. And that might be convenient to think you're done. Unfortunately, it's not. We now need to take that pressure and apply it to our actual structure. So we're going to use this CP factor, which is going to tell us on a windward wall what to multiply our pressure by leeward and sidewalls. So on the back side, it's 0.2 or 0.3. On the front, it's 0.8. On the sides, it's 0.7. You can have something more complicated for sloped roofs. But at the end of the day, we get pressure, which is our pressure we calculated before, times G sub pi, or GCP. So G comes from the gust factor we talked about earlier. C sub P comes from here. And then we have the internal pressure, which a lot of times we're just going to use the same as for the windward wall, times the CPI, which is 0.18 for a partial or for an enclosed building. But remember, it's plus or minus. So what usually happens is we'll add this, and we'll add this term, which becomes positive, and so we'll get a pressure, a total pressure on that face of the building that's more than just this pressure. So basically, we're adding the exterior pressure on a wall to the interior suction on the same wall. That's what this equation gives us. Okay, I think I'm going to split this up into 2 videos rather than make this super long. So I'll go ahead and pause this here.